Hello. Okay, so Alba here. I am going to explain how to count homomorphisms from one group to another. Possible homomorphisms, that is. Okay, so we have a homomorphism from G to H. Something that's important to know is that we know that the identity, for instance, in G, must map to the identity in H. And a very important thing, if we have an element G in left, it maps to phi of G. Now what's important here is that the order of phi of G must divide the order of G. So the order of the image of G must divide the order of G itself. So this is very important to note, and will help us count possible homomorphisms from a finite group to another finite group. So let's look specifically, let's consider something else. Also, if G is generated, say G is generated by a finite number of elements, perhaps 3 elements, then the homomorphism phi is determined by wherever it sends x1, x2, and x3. If it's, for example, it's generated by 3 elements. And so counting homomorphisms, this is great. So now let's say, for instance, that there is like m possible choices for where this can go, and n possible choices for where this can go, and say r possible choices for where x3 can go. So the total number of homomorphisms from a group G to a group H is m times n times r, just by the multiplication principle of counting. If m has m different possible places it can go on the right, and x2 has n different possible places it can go to there, and x3 has r different possible places, then these, the number of different homomorphisms is m times n times r. Okay, that's going to be very important in this example to follow. Okay, so let's consider the example where we have D16, which is a group under function composition, the dihedral group under 16 elements, mapping to Z12 under addition modulo 12. So we have, it's well known that the dihedral group of a 16 gon is generated by a rotation and a flip. And the rotation, if we rotate 16 times, we get the identity. And if we flip twice, we get the identity. And then we have a series of other ways to express the third structure identity. And that is that f times r equals r to the 15th power times f. So a lot of different equivalent ways to express this. So we know for sure that the image, I said before that the order of the image of an element G must divide the order of G. So, for example, the identity, wherever I send the identity in the left, must divide the order of the identity. But the order of the identity is always 1. So that's what forces, so the order of the image of the identity must divide the number 1. So there's only one choice for this order, because the order has to be a positive number, positive integer that divides 1. That forces the order of the image of the identity to exactly equal 1. There's only one thing on the right side that has order 1, and that's the identity here. But we already knew that. Homomorphisms take the identity here to the identity here. But this is one of the overwhelming reasons why that must occur. Okay, so let's consider the two generators. Remember, this map is completely determined, this map phi is completely determined by where it sends R and where it sends F. So we have an R here, and how many choices? Where can this go? And then we have an F here. Where can this go? Okay, so let's think about this. So, we know that the order of the image of R must divide the order of R. That we know. But what's the order of R in D16? Well, if I rotate a 16 around 16 times, I get the identity. So this number is 16. So I know then that phi of R, the order of phi of R must divide the number 16. So that forces the order of phi of R to be either the number 1, 2, 4, 8, or 16. So there's a number of ways to think about this. Using the homomorphism properties, 16 times phi of R. This is like phi of R plus phi of R plus phi of R. I say plus because phi of R lives somewhere in this world. So phi of R, phi of R, phi of R 16 times is the same as phi of R to the 16th. Using the homomorphism properties, I'm just recalling that, like for instance, phi of R plus phi of R equals phi of R times R. That's the homomorphism property. Phi of A plus phi of B is phi of AB. So here we have R to the 16th is just the identity. Whoops. So this is phi of E. But E in D16 is mapped to 0 bar and Z12. So this is 0. So now we have this equation, 16 times a number. 16 times something here equals 0. What are the possible things here that can equal 0? So there's multiple ways to approach this. We can literally go through all 12 elements and say 16 times 0, that's 0. Remember, this is lamp in the way? No. Mod 12. Mod 12. So 16 times 0, check, that's 0. So phi of R can be sent to 0. How about 1? 16 times 1, that's not 0 mod 12. 16 times 2, that's not 0 mod 12. 16 times 3, well, this is like a kind of a long way to think about this. We can think about it another way. We're looking for elements in here that have order 1, 2, 4, 8, or 16. Remember, Lagrange says the order of an element divides the order of the group. So a lot of these don't divide the number 12. The order of this group is 12. So we can already just say, cut out, there are no elements of order 8 here, because 8 doesn't divide 12. There are no elements of order 16, because 16 doesn't divide 12. 4 divides 12, 2 divides 12, and 1 divides 12. So now we can kind of just see in our head what is possible. 0 bar has order 1. Order 2, only 6 bar here has that. 6 plus 6 is 0. So 6 bar has order 2. If you think about it, for 4 bar, 3 plus 3 plus 3 plus 3 is 0. So 3 bar has order 4. There's another one. 9 bar also has order 4. If you just think about that, that works. And that's it. There are no other elements of order 4. No other elements. 6 bar is the only one of order 2. So these are the possible places that phi can go to, or can be sent to. So there are 4 choices for where to send R. And that's 0 bar, 6 bar, 3 bar, or 9 bar. Now let's do the same analysis for, F. So, phi of F, the order of phi of F must divide the order of F. The order of F is 2, clearly. So, this is a positive number, the order that must divide 2. So it's either going to be number 1 or 2. So phi of F, the order is 1 or 2. The order. So where are the possible images? 0 bar is an element of order 1. It's the only element of order 1. And 6 bar is an element of order 2. So that's it. There's 2 possible places that phi can send F to. So phi can go to 0 bar, F can go to 0 bar, F can go to 6 bar. So there are 2 choices for where to send F. So now you might be saying there's 8 possible homomorphisms from here to here, because there's 4 choices of where to send R and 2 choices for where to send F. No, there may not be 8 choices, because we still need to check the structural condition of the following. Remember, FR equals R to the 1 power less of 16, which is 15, the F. This is a general result in Dn. F times R equals R to the n minus 1 times F. And since n is 16, we have FR equals R to the 15th F. Okay, so since this is true, the homomorphism must satisfy this relation. So if I apply phi to both sides, then I use the homomorphism property. Phi of a product is the sum of the phis. Phi of F plus phi of R. And then, so that's what this becomes. This becomes phi of R to the 15th plus phi of F. Now what I'd like to do is just cancel that and cancel that. But I can't do that. I mean, if I had AX equals YB, YA, I can't just cancel those 2, because if the group is not necessarily abelian, like I can't cancel, multiply A on the left and A inverse on the right and A inverse on the left. However, if I had an abelian group, then this would be the case, and then I can cancel the A's, because I can hit A inverse on the left. So can I cancel these phi of F's? Well, I can, because this group, Z12, is abelian. So I can rewrite this line as phi of R plus phi of F. I can move those, and this is still phi of R15, sum phi of F. So then we get, I can cancel, or I can add by the inverse of phi of F on both sides. And then we're just left with phi of R equals phi of R to the 15th. But subtracting phi of R from both sides, I get 0 equals phi of R to the 15th plus negative phi of R. But negative phi of R is just phi of R to the inverse by the property of homomorphisms. And then we conclude that 0 equals phi of R to the 14th. Because R to the 15th times R to the negative 1 is R to the 14th. By the homomorphism properties, 0 is 14 phi of R. And this is all mod 12. Mod 12, I can reduce this 14 down to a 2, because 14 is congruent to 2, mod 12. So we're trying to solve the following.